Hello students, in this lecture we are going to see the breakdown of octet rule and Lewis rules, and then we are going to see what are ionic bonds, and we are also going to see another model of chemical bonding, which is the molecular orbital theory and abbreviated as MOT. So in the last lecture we started with the fundamental interactions that exist between the atoms when they come closer to each other to form a bond, and then we studied the first kind of the model of chemical bonding, the most primitive kind of model, which is given by Lewis. And we studied how we can draw the Lewis structures for simple molecules. The Lewis structures are based on the concept that we take the total number of valence electrons of the combining atom, and then we redistribute them in such a way that each bond between two atoms it gets two electron, and the remaining valence electron they are assigned to the atoms in order to complete their outermost shell or to form an octet. So whenever we have the breakdown of octet rule, we cannot apply the Lewis diagrams or Lewis structures or Lewis rules. So there are three exceptions mainly where we cannot apply the Lewis rules to form a Lewis structure, and we cannot explain the bonding by using the Lewis diagrams. The first one is the odd number of electrons, such as methyl radical, and this is because we have one of the rule in the Lewis diagrams that we have to assign two electrons, a pair of electron, to each bond. So when we have the odd number of electrons, we cannot do that. So therefore the Lewis rules break down in that case. So this methyl radical, you can see it has this dot on the top. This represents one electron, which makes the total valence electron as the odd number. The second situation is for group 13 elements that exist with less than an octet in the valence shell. For example, BF3, these are the compounds which are formed when this boron it does not have the complete shell in the complete shell in this molecule in BF3. Similarly, AlCl3. So if you draw their Lewis diagrams or if you draw their structures, you will see that there is no octet rule. Octet rule is not followed in the case of boron and aluminium. The third situation is the expanded shell structure for heavy elements, for example PCl5 phosphorus pentachloride and IF4-1 ion. So expanded shell structure means they have more than 8 electrons. D subshell is involved in these elements. So therefore we cannot follow the Lewis rules exactly. Now we are not going to see in detail these exceptions, but you should know that these are the cases where we cannot apply Lewis rules, but we still study the Lewis diagrams and Lewis structure because they predict 90% of the time the correct structure for the molecules. They are easy and simple to apply. Another important thing is that Lewis diagrams or Lewis rules they are mostly used to explain the covalent bonding in molecules. A covalent bond is formed when an electron pair is shared between two atoms. So it is mostly used to explain the covalent bonding in molecules. Another kind of bonding is the ionic bonding, and it is different from the covalent bonding. A very simple and most popular example is the formation of sodium chloride. As you can see here in this diagram, we have sodium ion which is formed by the loss of one electron, and chloride ion which is formed by the gain of one electron to form a negatively charged ion. So there is an electrostatic interaction or force of attraction between this positive ion and this negative ion, and this force of attraction is responsible for the formation of bond between these two ions. So this kind of bond which is formed due to the attractive force between the opposite charges is called as the ionic bond. So the sodium atom ejects electron and fluorine atom gains electron to form sodium plus and chloride negative ions. The two opposite charges are attracted toward each other to form a bond, and this is a very strong bond as well. We have also studied already in the previous lectures that ionic bonds are formed between the elements which have the low ionization energy and low electron affinity. They lie in the bottom corner of the periodic table, and the element which have the high ionization energy and the high electron affinity. So these form the negative ions. So and these ones they form the positive ions. So these negative and positive ions they can form ionic bond. So at an ideal interatomic distance, the attraction between the particle it releases energy when we have positive and negative ions and they come closer together at an interatomic distance. What happens that the energy is released and this facilitates the reaction and the formation of a ionic compound, for example, sodium chloride. Now, today we are going to see another advanced model of chemical bonding, which is the molecular orbital theory or MOT. And it is based on the quantum mechanics. And basically, you can see the orbital concept. So, it is based on the quantum mechanics because it involves the orbitals, the overlapping of the orbitals. It is more accurate in predicting the chemical bonding in molecules. However, it is complicated for heteroatomic molecules. Heteroatomic means when we have different kind of atoms, not the atoms of the same molecules. So for the heteroatomic molecules, it becomes complicated. As we go higher and higher, then it becomes complicated. So in this lecture, we are going to apply molecular orbital theory for simple and homonuclear molecules. Means we are going to see the molecules which will have the atoms of the same element. So let's start again with a simple example of the hydrogen molecule. And let's consider that we have two hydrogen atoms. This one hydrogen atom, it is represented by 1 SA, and you can see that this dot it represents the nucleus of the atom, and this circle it basically represents the orbital, or you can say our wave function of the hydrogen atom. And there is another hydrogen atom where we have this dot represents the nucleus, and this circle is actually representing the wave function of this second atom 1sb. This is the wave function 1s and it is for the atom b. Now, if we consider these as the wave function, these electrons, these circles are the wave function, then we already know from the previous concepts that the wave functions, like waves, they can interfere destructively and they can interfere constructively if they overlap. So what happens that when these two wave functions of SA, 1SA and 1SP, these two wave functions, when they overlap, then what happens that, for example, if they are added together and they interfere constructively, then they will form a new wave function like this. Combining these two atomic wave functions, it will form a new wave function. And you will see that this wave function has a probability density which is higher or which has increased in the center between these two nuclei. So earlier there was no wave function between these two nuclei. It was concentrated on the atoms, but after constructive interference you have some probability density between the two nuclei. And here you also want to know that this line, this blue dotted line, it represents the internuclear distance. Internuclear means the distance between the two nuclei. So this is the internuclear axis between the two nuclei of hydrogen atom. When the overlap constructively, the sum of the two wave function is represented by the figure. This one here I can show you. Now this new wave function that is formed is called as the molecular wave function, or we call it the molecular orbital because it is formed from the two atoms and a new molecule is being formed, and this is simply achieved by a process which is called as the linear combination of atomic orbitals. So the atomic orbitals they are linearly combining. And now what we call this molecular orbital, we name it as the sigma orbital. Sigma actually means something which is cylindrically symmetrical along the internuclear axis. Now we have already seen the definition of internuclear axis. For example, if you see this figure, you see this line is the internuclear axis, and this molecular orbital, it is actually cylindrically symmetrical above and below this nuclear axis. So that's why it is called as sigma, because sigma means this thing, that when you have something cylindrically symmetrical. So this is called as the sigma 1s. Sigma 1s because it is formed from the overlap of 1s orbital of hydrogen atoms. So it is named as sigma 1s orbital. So we also know that when we take the square of the wave function, we get probability density, which is represented by psi square. Here we are also representing it by the p. So if we can take the square of the wave function, we can also take the square of our this wave function, which is sigma 1s, the molecular orbital. It is also a wave function, so we can also take the square of this wave function. So probability in this case will be sigma 1s square, and we know that sigma 1s is actually the combination of 1sa plus 1sp, so we can also replace it by 1sa plus 1sp whole square. And if you see this, this is the formula of a plus b whole square, which can be expanded like this: 1sa square plus 1sp square plus 2ab. Now this is the probability density for our molecular wave function, and now we want to see that what happens to this probability density when we move along the internuclear axis, or we can say what happens to the probability density versus the distance along the bond axis. And we can plot a graph between probability on the y-axis and distance between the nuclei on the x-axis. So if you plot this, you will get a graph like this, where you can see we have maximum probability density at this point at the nucleus of A, and it is decreasing as we are moving away from the nucleus. And if you compare it with the probability density curves that we have studied already in the previous lecture, you will see that it is quite similar to that. Again, you see here, if you go to the nucleus B, you have maximum density here, and it decreases as we go away from the nucleus. But interesting thing is that we also have probability density in between the nuclei, and this is because of the bond formation, because of the constructive interference. This probability is between these two nuclei. So we actually want to understand that why this probability density is coming between the nuclei, because in the atomic state, when we have only the atomic orbitals, we did not have any intensity or probability density between the nuclei. So where it is coming from? So in order to understand how we are getting the probability density between two nuclei A and B, so let's compare this plot with the plot of the square of 1sa and 1sp without overlapping them, and then add them and plot it versus distance. So what we do not allow the constructive interference between 1sa and 1sp. What we do, we just simply take the atomic wave function of A atom and square it, and we take the atomic wave function of the atom B and square it, and then we add it. This is also a probability density because it is the square of wave functions. And if you plot this versus the distance, what we get is a plot like this. Here you can see this red one is actually similar to the previous one. The only difference in this case we get is this yellow line. The probability density is same across the nucleus and when we move away from the nucleus, but it is different between the nuclei. This yellow line is obtained in this case when we did not allow any constructive interference to take place between 1sa and 1sp. So this yellow line represents this thing, addition of two atomic orbitals and square of the two atomic orbitals. So you can see that if we do not allow the constructive interference, we are not getting this probability density between the nuclei. So basically, this probability density is coming because of the interaction of two wave functions of the two hydrogen atoms. So it just means we are taking two wave functions and squaring them and not allowing them to interfere, which is a different thing. And if we plot this sum, it's going to give a graph like previous, but different electron density between two nuclei. So this is the yellow thing. So it means the probability density that we are getting is because of this term in the equation. If you recall the previous equation, you see we have 2ab in this equation as well, because you see we have already compared by plotting 1sa square plus 1sp square with this one, and they are not similar. So it means the extra density, this one, is coming because of the additional term which is present here, 2ab. So this is giving us the additional probability density between the two nuclei when we have constructive interference. Now what we can do, we can also draw the energy level diagram for the atomic orbitals when they are combining to form the molecular orbital. So when we draw the energy level diagram, we always have this line which shows the increase in energy, and this is the atomic orbital for A atom, and this is the atomic orbital of the B atom, and they are both of the same at the same energy level. When they interfere constructively, a new molecular orbital is formed, which we named as sigma 1s molecular orbital. And you see that it is like actually lower in energy as compared to the atomic orbitals. You see here it is lower in energy. Now what we do next is, once the molecular orbital is formed, we are going to fill this molecular orbital. So we already know that we have one electron in one hydrogen atom, and we have another one electron in the other hydrogen atom, and one electron and one electron, they combine together to form a molecular orbital which has two electrons, so that we have complete shell by sharing of these two electrons in the hydrogen molecule. So once we allow the constructive interference to take place, sigma 1s is a new molecular orbital having lower energy, and the chemical bond is formed due to lower energy, and it contains two electrons. So here is also one of the important concepts that I repeat again and again, that when you have a chemical bond formation and new stable molecule is formed, it should always have the lower energy than the atoms, so that it is a stable system. So since the orbitals are waves and they can interfere destructively as well, because we have seen already that the waves, they interfere constructively and destructively. So let's see what happens if there is a destructive interference between the two same hydrogen atoms. So we have this again, one A hydrogen atom and this B hydrogen atom. We are representing the wave function by circle, and because we are having destructive interference, we represent it by the negative sign. So the result is that when these two regions, they come closer together and they overlap, this region overlaps, then you see there is no probability density between the two nuclei. It is there here in this, on this side, but there is no probability density between the two nuclei, because this is the region which is overlapping. So we will only have the effect of constructive or destructive interference here on the center, in the center between the two nuclei. So you see this is purple line which represents actually the node of the wave function. So in destructive interference, the two overlapping parts of the wave function will cancel each other. The result is that the molecular wave function will have a node in the center, because the center portion of 1sa and 1sp are cancelling each other. So this wave function is called as the sigma star 1s anti-bonding molecular orbital. Again we name it as sigma because it is, again you can see it is cylindrically symmetrical along this internuclear axis. It is same on above and below the axis. So it is cylindrically symmetrical, but the star represents that it is anti-bonding molecular orbital. So how do we know that it's anti-bonding molecular orbital? It's not forming any, it's not contributing to the bond formation between the two atoms. So let us again mathematically prove it. We have probability density, which is sigma star 1s square. We have the wave function, we square it, and we get 1sa minus 1sp into 1sa minus 1sp. Of course, this sigma star is forming because of these two, 1sa and 1sp, subtraction of these two orbitals. So again, you know that it is actually the formula of a minus b whole square. So if we expand this formula, you get 1sa square plus 1sp square minus 2ab. So this is similar to the previous term, but we have a minus 2ab term here. So this minus 2ab term is actually contributing to the not present, no probability density between the nuclei. And if we represent it by the graph, probability density versus distance, you will get something like that. Here it is similar here, around the nuclei, but in the center you see this yellow line now represents the antibonding molecular orbital, sigma star 1s. This red line is again for the sigma 1s when you have constructive interference, and you see this yellow line is actually the destructive interference. When you see the probability density between these two nuclei A and B, it actually almost goes to 0. So it is even lower than the case when the two atoms were not interacting. As you have already seen, that we also compared the case when the two atomic orbitals they do not overlap, and we just add the square of them and we plotted it. It did had some intensity which was theoretical actually, but this anti-bonding molecular orbital is giving actually zero energy, zero probability density between the nuclei. So let us plot it again, the energy level diagram. And this is if you see this diagram, the energy is increasing on the upside. We have 1s a and we have 1s b. This is the bonding molecular orbital sigma 1s. The anti-bonding molecular orbital will be higher in energy, and it's represented by sigma star 1s. And again you see that there is no electron in it because we have only one electron in the two atomic orbitals, and we always follow the off-power rule again for filling the orbitals for atomic orbitals as well as for the molecular orbitals. So the off-power rule is that we have to fill the orbitals from the lower energy to the higher energy, and we also know that each orbital can have two electrons, so we cannot move to the higher orbital until and unless we have filled the two electrons here. So these two electrons will come here and there is no electron in the sigma star 1s. So what is actually the significance of this distance between the bonding molecular orbital and the anti-bonding molecular orbital? So if you recall our previous lecture, you will see that it is actually the same bond dissociation energy that we evaluated through this interaction energy curve for the hydrogen molecule. So this bond dissociation energy will be same as this difference of energy from the molecular orbital theory. Now, two more things that we can do in the molecular orbital diagram is that we can also write the electronic configuration of the molecule, not the atoms, the molecule, because we write down the electronic configuration of the atoms as well, but in the MOT we can also write down the electronic configuration of the molecule after the molecular orbital is formed. So in the case of hydrogen, we have sigma 1s, and 2 here represents the 2 electron, not the square of it. So we have a sigma 1s orbital with 2 electrons, and sigma star 1s which we have 0 electrons in. And we can also find out the bond order, that is the number of bonds between the two atoms, which is determined from this formula, that is half of the number of electrons in the bonding molecular orbital minus the number of electrons in the anti-bonding molecular orbital. So if you calculate it, we have 2 electrons in the bonding minus 0 electrons in the anti-bonding, and we divide by 2, we get 1. So we have 1 bond in the hydrogen molecule. So let us draw the molecular orbital diagram for the helium molecule and see whether a bond is formed with the helium atoms or not. So again, let us first see that we have the electronic configuration of helium atom, which is 1s2. That is, each helium atom has 2 electrons in the first shell and it has a complete shell. So if we have 2 helium atoms here, if you see this diagram, 1sa is the helium atom 1 which has 2 electrons, and 1sp is the helium atom 2 which has 2 electrons again. And these two atomic orbitals interfere constructively to form sigma 1s, and they interfere destructively to form sigma star 1s. So let's start filling the electron. One electron comes from this helium atom here, and one electron from here, this atom. So we have complete 2 electrons in sigma 1s, but we have remaining 1 electron here which goes to the sigma star 1s. So we also have 2 electrons in the antibonding molecular orbital. Now let us write down the electronic configuration of the molecule. Helium molecule is, you can see we have 2 molecular orbitals, sigma 1s which has 2 electrons, and then we have sigma star 1s which has 2 electrons. So we always write these molecular orbitals in the increasing order of energy. Now let us find the bond order, which will give us the information that whether a helium molecule is formed or not. So we have the formula 1 by 2, that is half of the number of electrons in the bonding molecular orbitals minus number of electrons in the anti-bonding molecular orbital. So we have 2 electrons in both, and if we solve this we get 0. So we have 0 bond order in the helium molecule, and it means that we have no bond between helium atoms, and helium molecule is not formed. So this molecular orbital theory, it correctly predicts that helium molecule is not formed because it is a noble gas and it has a complete shell. Now let us see another example, lithium molecule. Lithium is from the third group, and we have its atomic number 3, and we have 3 electrons in its orbitals. We have 1s2. First shell has 2 electrons, and the second shell has 1 electron. The second shell is incomplete. Now let's suppose we have this 1sa is the lithium atom 1 and 1sp is the lithium atom 2, and we have 2 electrons here because 1s2 is filled. So they will interfere constructively to form sigma 1s, and they will interfere destructively to form sigma star 1s. If you fill the electrons again, you will have 2 electrons in the sigma 1s and 2 electrons in the sigma star. This is similar to the helium, but we have another 2s orbital here, so we will also draw the 2s orbital containing 1 electron. But you should remember that since the 2s orbital is higher in energy, so you will always draw this 2s orbital above the 1s orbital. So this is the 2s of the first lithium molecule atom, and this is the 2s of the second lithium atom. And again they constructively interfere to form sigma 2s. So here you will write sigma 2s because it is the 2s orbital. And this is the sigma star 2s, which is the anti-bonding molecular orbital. So again, if you fill the electrons, 1 electron comes from here and 1 electron comes from here, and you have a complete sigma 2s, but there is no electron in the anti-bonding molecular orbital. So now let us write down the electronic configuration of lithium molecule, which is lithium molecule has sigma 1s, which has 2 electron. Here you can see sigma 1s 2 electron. Then we have sigma star 1s, which has 2 electron. Here you see sigma star 1s, which has 2 electrons. Then we move to the sigma 2s, which also has 2 electrons. Here you can see it. Then we have sigma star 2s, which has 0 electrons. So this will be the electronic configuration of the lithium molecule. Now we find out the bond order, which is again there half the number of electrons in the bonding molecular orbital minus the number of electrons in the anti-bonding molecular orbital. So we have 4 minus 2 is equal to 1 because we have total 4 electrons in the bonding molecular orbitals. 2 here and 2 here, so they will be 4, and we have only 2 electrons in the anti-bonding molecular orbitals. So 4 minus 2 divided by 2 we get 1. So it means we can have one bond between lithium atoms to form lithium molecule. So 2s orbitals are actually the same shape as the 1s orbital, and therefore they interfere constructively and destructively in the same manner. But the 2s orbitals, they are higher in energy as compared to 1s. Now let us see the example of beryllium molecule Be2. So beryllium atom has 4 electrons in total. Beryllium has atomic number 4. Let's write down first the electronic configuration of beryllium atoms, which is 1s2, 2s2 and 2p 0. The 2p has 0 electrons. So this is not a complete shell because 1s2 is a complete shell, but 2s2 also includes the 2p orbitals, and therefore when we have 2s2 electrons, it doesn't mean that the shell is complete. So it has a tendency to react and to form bonds. Now let us draw the molecular orbital diagram. We have 1sa of the beryllium 1 atom and then 1sp of the second beryllium atom. Both have 2 electrons. We form sigma 1s and sigma star 1s and fill it just like the helium atom. Now we move to the 2s, which is higher in energy, and it also has the 2 electrons. So we fill the 2s, sigma 2s and sigma star 2s. So we fill it, and again you see that all the molecular orbitals are filled. Let's write down the electronic configuration of beryllium. We have sigma 1s, we have 2 electrons here, sigma star 1s, again 2 electrons, sigma 2s has 2 electrons, and sigma star 2s has 2 electrons. So bond order is 1 by 2 into number of electrons in bonding molecular orbital minus number of electrons in the anti-bonding molecular orbital. which gives us 0. So it means that beryllium molecule is not formed. Beryllium and beryllium atom, they do not react to form beryllium molecule, but it does not mean that it is a noble gas like helium. It does form bonds, it does react with other elements because it does not have the complete shell. It forms many other compounds like beryllium chloride, and there are many other compounds, but it's not like it is a noble gas. It is just that the beryllium molecule is not formed in this way.